If there was a technology that could digitize your thoughts into movement commands, what would you do with it? Maybe you would want to control a robot by attempting to move your arm. Maybe you'd want to use the robot to fist bump Barack Obama. Why not? Hey, maybe you would want to use the technology to control a computer. And by imagining your arm movement and then performing a grasping motion, you could click on things as they appear in the UI. You might want to use the same modality to spell things out and communicate at about 5 words a minute. An even faster way to communicate would be to imagine how you're moving your fingers when you're performing your own handwriting and you're spelling individual letters. They appear on the screen. The hand is not really moving at all, and yet the signals from the brain are being decoded into text at around 20 words a minute. But an even faster and more intuitive way to use the technology would be to attempt to speak words. And as you're attempting to speak words, the neural activity is encoding them, and they can be again decoded into full words. This kind of technology works now at a rate of around 65 words a minute, about half the speed at which I'm talking to you right now. And it's, thanks to large language models, incredibly accurate. The word error rate of this technology is less than 10%. That's approaching the 5% mark of Alexas and similar devices that we use day to day. That's really remarkable. But here's the catch. The technology is incredibly invasive. So, blood warning, anybody who doesn't like blood, cover your eyes for a couple of moments. All of the demos that you saw have been performed using this technology called the UCAT array. In fact, here are 2 of them. Each one of these chips has up to 100 electrodes that penetrate the upper layers of the cortical areas that encode movement, and they extract the neural data into a third-party computer that decodes it into behavior like speech or movement. And overall, the system is called a brain-computer interface. Now, the UCAT array has been designed 30 years ago, and it's still the gold standard to decode behavior from neural activity. But it has some drawbacks. It has been used in over 40 participants and 40,000 days in operation, so it's a really good track record. But the limitations of the technology motivate many startups to start their own device manufacturing companies, and over $2 billion have been invested in just 9 startups that are trying to improve the status quo, make the technology more biocompatible, make the technology less invasive, make the technology more powerful by recording from a larger amount of channels. And here's an example. This is Neuralink. Their R1 implant, or robot, is implanting individual electrode threads, and in 15 minutes it will implant over 1,000 channels into the motor cortex. By the way, this is a simulated brain, so you can uncover your eyes from their demonstration. But the implant is then replacing part of the skull and stays shut, kind of cosmetically invisible. This is precision neuroscience. In their technology, they're using a microslit technique to insert the implant on top of the cortex, not penetrating the cortex at all, but they are underneath the dura that protects the brain. And they again record from 1,024 channels. And lastly, we have Synchron. This is the least invasive among all. Through the jugular vein, the implant is inserted to sit right next to the areas that encode movement, and with 16 channels, it's recording the neural activity after it fuses with the vascular wall. I had to break it to you. You all here are not going to be the first users of this technology. To paraphrase Mary, for people like you and I, this technology makes things easier. You don't have to move your muscles to perform some actions. But for people with paralysis, this technology makes things possible. And when I interviewed some of them, the overwhelming reflection that I received is that after such severe paralysis, they want to restore their expression. They want to get back their agency over their own life. They want to regain the independence that they've had once, their privacy, their social participation. And in fact, all of the participants you saw in the first video reel were people with severe paralysis. There's over 360 million people with speech and motor impairments. 21 million of them are so severely impaired that they're restricted to an electric wheelchair with a postural support and speech aids to interact with the world. And 1 million of them, 1 million people around the world, are what we call locked in. They can't move anything but their eyes. Yet their mind continues to work just fine. And these words that I mentioned earlier, agency, expressivity, they are nice words and they're powerful words, but they are not product requirements. When we're building these technologies, these words need to be broken down into specific product requirements that encapsulate the clinical outcomes or the outcomes, the end user value of this technology. And to my surprise, nobody has done that. There has not been one proper breakdown of what is the end value of this technology that people are going to be using it for. And so I decided to change that by writing this book, Transcend the Limits of Body, Time, and Space. In the first chapter of this book, I run through over 400 different requirements from the clinical literature that's evaluating quality of life outcomes for people with severe paralysis. And I combine them into a set of requirements that these implanted brain-computer interfaces should deliver on. In the second chapter, I highlight how the speech decoding and motor decoding for the movement has made strides in the recent years. What is possible, what is still not possible? How can we mature the AI that's decoding the brain? And also, what is the state of the art? What can we know? What can we not know? That's very important to motivate the kinds of outcomes that you can deliver for patients. And so in the third and fourth chapter, I introduce a novel kind of application, an application that really is underrepresented by anybody who's building these kinds of brain-computer interfaces. And yet I think it's most commercially viable, it's incredibly technically feasible, it's cheap for the end user, and it's incredibly valuable. Before I get to that, I want to tell you what these usual applications are. So you have a technology of brain-computer interface that is extracting neural data and converting it into some behavior, but really the end user value comes from the application of that technology. And two favorite applications are, one, robotic applications. So prosthetics that you can control, as you saw in the first video. Now, robots in real world, exoskeletons, prosthetics, real world is really difficult to manipulate. And these technologies are therefore quite immature. And once they are not going to be immature, they're going to be prohibitively expensive. The device cost for a prosthetic arm that integrates with the brain is estimated between 50 to 150,000 pounds for one device. And good luck finding reimbursement for that. The other technology, the other application that is being favored by implant manufacturers is that of controlling a computer cursor, right, to spell things around. As we saw in the demos, this dates back, these kinds of demonstrations, 10 years or more. Now, it's a big shame to compress and dumb down such rich decoded signal about the behaviors that we're performing into just mere 2D movement and maybe click, and that's associated with it. It's a shame because we can decode more, and we can therefore give people more expression back than a simple movement of a cursor. In fact, non-invasive modalities are really competing with these invasive kind of applications. Here is an example of Jeff. Jeff had ALS, and he died in 2020. He wrote his book, a whole book, using eye tracking device, spelling letter by letter, and he did that successfully. But what really would a tablet that you can control with your brain that's highly invasive or less invasive but still invasive, what would that give you more than an eye tracker or a similar non-invasive device? And so in the third and fourth chapter, let's get into it. We introduce virtual reality as being the number one application that makes these technologies scale, these brain-computer interfaces available for everyday users. In virtual reality, embodying an avatar means that you can take the decoded signals of the speech and of the movement and place them on the arms and mouth of the avatars as you're interacting with the virtual world. This way you can reconnect with your own expressions, reconnect with your loved ones if you want to meet them across the globe, reconnect with your hobbies, with your work, with your communities. You can do it all in the metaverse, so long as we can map those decoded behaviors onto the virtual avatars. And you can do all of that without appearing to be paralyzed, because the avatar is a great equalizer. And so in the third chapter, I go through a large comparison of over 100 experiences that delivered the kind of quality of life for each of the requirements that I outlined. I would like to give you a few examples of those, just so you can imagine what it is like to be in the metaverse. So first, we have Gravity Sketch. This software is used for 3D modeling, and big brands like Ford use it to 3D model cars. Here the artist is creating an elephant that can be exported, 3D printed, shared with anybody, anywhere. As long as you can map the decoded motion of the arm onto the motion of the controller and finger movements onto the buttons of the controller, you can also, with severe paralysis and with brain-computer interface, create these kinds of models. I think that's really quite impressive. It takes only 7 minutes for the author to create this model here, which it would take about twice as long if you did it on a 2D screen. Here we have an example of a class that's being given inside of Metaverse. It's a signing class, and these are all real people that are wearing headsets and interacting with each other from around the world, learning new things, and lectures can be done entirely in the Metaverse. You can meet other people who have severe paralysis despite long location differences. And in here, you're not restricted to having these educational talks or talks of any kind or meetings of any kind inside of Metaverse only. Here you're having a user demonstrating a popular application from Microsoft. And Teams, which is what we're having the call on now, is a video conferencing app like Zoom or WebEx. Here, there's a native integration that's already out there that people from the Metaverse can embody their avatars, see through their avatars, people who are using the desktop. So you can join on any calls that you're currently doing in your avatar form from the Metaverse and interface with people who are not in the virtual reality. And in this way, you have an even wider range of activities that you can do, kind of cross-reality interface. And in this last video, I would like to show you just one application of the tens of thousands of applications that are available in the virtual reality. And within that one application called VR Chat, I'd like to show you a few worlds among the thousands that are available that all of you can explore at relatively low cost.
What is reality? Obviously, no one can say because it isn't words. It isn't material, that's just an idea. Reality is... The point cannot be explained in words.
These worlds have been created by people like you and I, uploaded, and then anybody who has a headset can go in and explore them. You can be there alone with other people if you want, and that's just one application of the thousands. Now the big question now is, how do we do it, right? We've seen that what the neural decoders can do, what the brain-computer interfaces can do. We've seen that in the first beginning. We've kind of talked about what patients and the first users of this technology would like to do. We talked about how virtual reality can help deliver the kinds of outcomes that they want from this technology. And again, the question is, okay, how do we do it? And this is why we started UKAT. How do we guide the patient? How do we guide the person with severe paralysis into using these kinds of applications that I just described? I think the most natural, best way to do it is with the help of an avatar. An avatar is a personal avatar like UKAT here, somebody who you can trust, somebody who's keeping you company, somebody that tells you about how you can use the new technology that you've been equipped with to your most advantage. And in a similar way to how your parents are guiding you on your early stages of life, UKAT is guiding users on how to use the brain-computer interface. Specifically for our prototype, we have focused on speech. As I showed you earlier, speech has skyrocketed as a modality that allows us to decode information at such a rate that was never possible before, and that's thanks to large language models. I think that speech, BCIs, are going to be the first proper use cases for these high bandwidth brain-computer interfaces I showed you earlier. And so I think when you design any software, it needs to have three qualities. It needs to be useful, it needs to be usable, and it needs to be beautiful. For the usability side, I'd like to show you the first two modules. This is the first time we're showing it publicly, that replicate exactly the setup in the speech brain-computer interface trials that individual participants in those trials go through to master to calibrate their model and to master their speech brain-computer interface. They're kind of training exercises for the patients, for the participants to be engaged with, and let's have a look.
When the dots disappear, repeat the word on the top half of the screen.
Computer.
So a word is presented and you're attempting to repeat that word. By repeating it, you produce a particular activity in your premotor cortex in this case, and that activity can be decoded into speech. This is a closed loop trial for those who are more academic. And if you get it wrong, perhaps you should try again. So we made that so that there don't have to be 4 or 5 researchers in the same room, while thousands of participants will have to be using this technology to commercialize it. You know, in order to get the nod from regulators like the FDA, you need to do trials with many, many participants, and this is the way we automate their training of their models. In fact, the person that you saw whose speech was being decoded at 65 words a minute, Pat is her name, she had to repeat over 10,000 sentences to calibrate her decoder, and that took weeks and weeks of concentrated labor. So we're trying to make that as fun as possible and as engaging as possible. So after you graduate from the first module of repeating words, you go to repeating phrases. All right, that's quite similar. Now, beyond usability, we want to make this technology useful. We want to give people back this sense of agency. And so for that, we designed another module where you can explore this virtual world that you see in the background with just the power that you've acquired by training with this application and by calibrating your motor BCI, motor brain-computer interface decoder. It takes the shape of a menu.
If you say, "Hey UKAT," I'll show you a list of helpful commands so you're in charge of your time here. Try saying, "Hey UKAT."
Hey, UCAT. Daily check-in.
So here you have a menu, you can explore different parts of the world, you can go to different places. This way you get agency back over what's happening to you, maybe for the first time in years. And then the last module that I would like to share with you in this quick rundown is one where you get to write notes, to express yourself freely, perhaps for the first time in years, where we ask a set of standard questions about their quality of life, or kind of the same every time, but users can take this as an opportunity to kind of take notes and express themselves, express their ideas, write them down if they want for later.
You can use this exercise as a way of tracking your moods. How are you feeling today?
I'm doing great. Yes.
What's the weather like?
It's a little...
Okay, so you might be wondering,
What do you
oh,
have?
you have one word, don't you, UKAT?
I'd like to play virtual golf.
So you might be wondering, okay, do we have a brain-computer interface that's giving us the outcomes here, the words that you're seeing? No. The way that we implemented our prototype is that as you're speaking, the microphone in the headset is picking up what you're saying. That is being sent as voice, as an audio file to a third-party server that converts the voice into text. We receive the text and we use the text to command the entire virtual world. And in this way, it's exactly the same way that we would use a third-party brain-computer interface from one of these trials, except to not use a third-party NLP, natural language processing algorithm, but have the text of speech coming from the brain-computer interface decoding pipeline. So in this way, we found that it could be really, really easy for us to partner with clinical partners who want to test our technology in the wild and see how it performs. You know, this is a very good simulation of how it would perform if the source was coming from the brain-computer interface, source of the speech. Now, on the beauty side, we had conducted several interviews with future users of this technology, and we decided that the good way to start, after talking with them, is to have this kind of serene environment where people actually want to come back to. You know, they want to come back every day and practice more. But in the future, there will be more worlds. Now, I'd like to show you one more module that I kept in the back before I conclude. It's important that you cannot just express yourself in a kind of static way, express your thoughts, but if you really would like to get your life back, your expression and your participation back, you want to simulate a social situation. You want to get a conversation going with somebody, and we built a module that allows you to do just that. So, hey UKAT, what's next?
What happens next?
Next, you'll learn to master your virtual body so you can explore the metaverse. Till then, have fun chatting with your speech BCI.
That's right, UKAT. We are also working on the next iteration of the product where metaverse really makes sense, but once you can control your arms when you're embodying the avatar. So speech is great, but to take advantage of all the applications that I showed you earlier, you need to be able to decode attempted arm movements, attempted finger movements and gestures, and map them onto the standard ways of how people are using controllers and hand tracking now to interact with the metaverse. And that's the next generation of UKAT that we're going to build out in the future. I should also mention one more thing before I conclude. While we were writing the book and while we were building this prototype, we were constantly asking this question of what can software do better to accelerate the commercialization of these brain-computer interfaces. And besides virtual reality, which is a great application for the first generation users, the decoders themselves have some shortcomings of their own. They work within the context of a study. They generally work for one participant. They require a lot of time to train. And they're not robust to everyday scenarios. They're not robust to disturbances. They're not robust to internal thoughts and require a lot of concentration. And we thought that we could improve on the performance of these decoders, specifically by applying best practices from other machine learning domains that manage, process sequential data like neural data. And we decided to work on an open source model for decoding speech. And we're improving the accuracy as we speak, and I'll share the results with you in the next talk. But it takes a village. Okay, it was just a handful of us. Half of the team is in this room. We need a lot more people. And we have made it so that all of our software, this XR software you saw, the book, everything is open source. The decoder is open source. So anybody can use this in their research if they want. They can contribute to the code. They can find it on our website. And we together, if we all work together, if we all contribute to this very, very exciting next milestone in how we interact with technology, we can get this technology out to the people who need it most this year. Thank you.